Pronto? Hello, 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 hello. Can we start? Is Remo Ruffini speaking?
Yes, we can start.
Chris, are you there?
I'm here.
Oh, yes, I see you. Good, 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 good. Okay, where are you today?
I'm in Los Alamos in New Mexico.
Fantastic. We are in Pescara. We missed you. We hope you come here and we come there as soon as possible. Okay, can we start then?
You need to let me share my screen, I think.
Okay. Hello? Yes.
Okay.
Here we go. Go.
So,
I will give you a signal 5 minutes to the end.
Sounds good. So I wanted to talk about kind of where our picture of what's happening with core collapse supernova and its engine, so focusing on its engine, and what kind of observations have kind of firmed up the picture that we have. And here I show what got us going on the engine in the first place, which is the explosion of supernova 1987A. And one of the features that has kind of guided us in the last couple decades has been the asymmetries that we see in the explosion. And so you can see these asymmetries as 1987A is exploding outward. So you see the ring and then the bright supernova, but with time, the ejecta looks quite asymmetric. And at 2016 or 2012 even, it's pretty obvious the asymmetries that you're seeing. So I want to kind of go, this is a good example of how science progresses and science, especially in astronomy, progresses. And so I wanted to give a little overview of what I mean by that. When in the late 60s, early 70s, there's big arguments about two different standard engines. There was the some kind of core collapse, the collapse of a normal star down to a neutron star. And Bada and Zwicky had proposed that in essentially, well, quite a few people had, as soon as they understood what a neutron star could be or what the neutron was, they hypothesized that they could have a star collapse down to that, and the potential energy release could power a big explosion. The other model, which I usually attribute to Hoyle and Fowler, is a thermonuclear explosion of a star. So you take a white dwarf and you start to cause fusion of the core, the carbon-oxygen core, into nickel-56, and that the energy released in that fusion can power a strong supernova. And in the 60s and the early 70s, Sterling Colgate and Dave Arnett were two of the modelers that argued a lot about which one was the right model. And so they would attack, there was a series of papers, and this was maybe something that Chandrasekhar helped drive, but there was a series of papers where they would look at different properties of the explosions of the different models and try to exclude one model or the other. And this gets into two different philosophies that we have in astrophysics and science in general. And one is Occam's razor, which is, I guess my favorite way of describing it is from Isaac Newton, which is, we are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. So if you have a model that's sufficient to explain all of the data, you don't need to have a whole bunch of other models to explain the data. In contrast, there's one that Kip Thorne pushed with Anna Zitkoff when they were first proposing Thorne-Zitkoff objects, and that was a quote that they got from a book called The Once and Future King from T.H. White. And And it's a book about, it's a King Arthur story. And in that story, Merlin turns King Arthur into different animals, and they learn different he learns different political systems in those different animals. And in the kingdom of the ants, there was a sign out front of the anthill that said, "That which is not strictly forbidden is mandatory." So this is a contrast, because it says, if you can't disprove a model, then nature will make it happen. And so those are kind of the two different contrasting philosophies that we use in science. And in this case, Dave Arnett and Sterling Colgate tried to disprove each other's models and could not. And now we know that both engines exist. So we both have thermonuclear supernova and core collapse supernova. But you can also apply that as you go down to the core collapse idea. The question then comes, what is the engine, once you collapse down your core, how do you get that potential energy that you've released collapsing down to a neutron star to drive an explosion? And so there's the model that Colgate and White proposed, which is that the neutrinos that are trapped get trapped in that neutron star. As you collapse, the potential energy goes to heat and then is conveyed out of that neutron star in the form of neutrinos. Those neutrinos drive an explosion. And that's that engine has evolved, and the current version of it invokes convection above that protoneutron star to help make the energy transport more efficient, or actually make the energy conversion into an explosion more efficient. The other model that has been proposed is if you have a massive star and it collapses down to a neutron star, but it's spinning, you can have a jet driven from that accretion disk. So those are the two standard models. Then there's a lot of other models that have been proposed, but I want to just discuss those because those are both proposed to explain normal supernova. So I'm going to focus on normal supernova. I will touch a little bit. If you're going to gamma ray bursts, you do need to invoke, you go to a more and more selective models because they are select creatures. But for normal supernova, these are two competing models, and I wanted to go a little bit over how those models work. So before I start, I thought I would talk a little bit about stellar evolution and go in a little bit on, the common diagram that anybody who's worked in supernova or stars knows completely well, and they show it and they assume they assume that it conveys the same information to anybody else as it would to them. And it does convey a lot of information, and I'm not going to be able to cover everything on this diagram that I could, because that would take almost an entire talk in itself. But I want to use it to focus on what we care about when we're talking about core collapse supernova. So the diagram, the x-axis is the log time until collapse. And it's probably hard to see the axes, but it's on the very left is 10 million years. This is a 22 solar mass star. On the very left, it's 10 million years. It goes through down all the way to 10 to the -8 years, so less than a second before collapse. So it can show all the phases of the life of the star. On the y-axis, this is the enclosed mass of the star. So the star is 22 solar masses. So the top of the star, there's a black line there. It's showing the envelope is at 22 solar masses. One of the features of this diagram is you can see what mass loss happens. So there's mass loss during the hydrogen burning phase, which happens from 10 million years to 1 million years. And then there's an extensive mass loss when you expand into the giant phase and you have helium burning. And so the star actually, from this diagram, I can see that the star goes to less than 15 solar masses by about 100,000 years before collapse. And then it remains at that mass until collapse. The part that we care about in core collapse supernova is the core. And so the core is this inner, if you look at the lower part of the diagram, so the inner 5 solar masses is this lower part of the y-axis, And you can see that's where all the action's happening. That's where you have hydrogen burning, helium burning, and then you go through a phase of carbon burning, carbon shell burning. And you can see that the star goes through a series of burning phases, and it happens only just before collapse, right? So a year, it's done carbon burning up until a year before collapse. Then it starts oxygen burning less than the last year of its life. Silicon burning happens in the last few days of its life. And it's building up this iron core. And it's how these burning phases behave that determines the fate of the star. And one of the biggest uncertainties we have in understanding stars is during these burning phases, exactly how you do the mixing and the convection can dramatically change the fate of that inner core and that burning. So that's where it gets difficult. But when we're studying a supernova, unfortunately, that's all that matters. The outer material won't affect the engine at all. It's just this innermost material. So the lower part of that graph, the lower bottom, 10, 20% of that this graph is where the action happens as far as a supernova engine person is concerned. So what happens is you build up this iron core. It continues to build up. It has some entropy, and it's supported in part by that energy, so that the entropy, the heat, the thermal energy, but it's also mostly supported by electron degeneracy pressure. As you build up, do that silicon burning, and you're doing silicon shell burning and adding mass to the core, the core starts to contract. And at some point, the core has contracted so much that you start to get iron to capture onto protons, emitting a neutrino and becoming a neutron. So you start to neutronize that core, and that removes the electron degeneracy pressure. At the same time, you get to such high temperatures that you start to dissociate the iron atoms in the core and return them back into alpha particles, into helium atoms. So all that energy you had gained by burning, to going through these different burning phases, you're now losing because you're dissociating the iron. And so you're actually losing your thermal energy, you're losing your electron degeneracy pressure, and so the core starts to collapse or contract more. And as it contracts more, it accelerates that iron dissociation, it accelerates the electron capture until you get a runaway collapse. And so the image on the left is radius in 1, 10, 100, and 1,000 kilometers, and velocity in a fraction of the speed of light of this collapse process. So it's collapsing in, the core is collapsing, and there's a portion of the star, the inner portion of the star starts to fall inward at about 1/10 the speed of light. It does this until the neutrons gets so dense that the neutrons are degenerate. And so neutron degeneracy pressure, nuclear forces start to halt the collapse, and the star bounces. So no matter what engine we're looking at, that is going to be the first step of it. It's going to collapse down nearly at 1/10 the speed of light, and then it's going to reach neutron degeneracy conditions, and it's going to halt the collapse, and there's going to be a bounce. And that was the original core collapse engine proposed, was that bounce would be enough to produce a supernova. Unfortunately, that bounce shock, as it moves out, most of its energy is still in neutrinos, and as soon as it becomes optically thin, it loses its energy, and the bounce shock stalls. So the bounce shock model does not work once you put in all the physics. So you get a condition where you've collapsed down to a neutron star, you've had a bounce, and then the bounce shock stalls. And so now this is where the two engines, either a accretion disk model or this convective engine, will start to differ in their behavior. And it all is due to what is the angular momentum in the star. So one way to try to get a handle on what the angular momentum is during these stellar models. Again, I told you these mixing can play a big role in shaping what the core looks like. It also shapes how much angular momentum do you have. And so different models make different predictions. And on this plot here, I have the enclosed mass of the star. So at 0, the inner left is the the center of the star, and I'm moving out to 2, 4, 6, 8, 10 solar masses. For a 15 and a 25 solar mass star at collapse, the dotted lines are, so the blue, let's see if I can, the blue is the 15 solar mass star, the green is the 25 solar mass star. The dotted lines come from some models by Menet and Médère, where they did not do any transport from magnetic fields at the boundary between different shells. So at the carbon helium shell boundary, there was no magnetic field coupling between those layers. If there's no coupling, you can end up producing a very rapidly spinning star. And these stars would produce sub-millisecond pulsars. They would produce black holes. If they collapse to a black hole, they would produce a black hole with spin values above 0.95. And they also would produce a huge accretion disk around the neutron star that I formed. And this red line is the angular momentum needed. So the y-axis is the log of the angular momentum in centimeters squared per second. The red line is the angular momentum needed to form a disk, to produce a disk in this model. And so those models all produce a strong disk. If I add a simple dynamo, which Hager and Woosley did with Higgs-Sproit, you see that I lose enough angular momentum that I actually can't form a disk. There's only a little bit of material that has enough angular momentum to form a disk, and it's well above 2 solar masses. It's actually above, it starts to become above 3 solar masses. And so to get a real disk with those models, you're probably going to have a disk around a black hole. Even worse, Jim Fuller has done some models with MESA using a even more strict dynamo. And with that model, he has even 1 to 2 orders of magnitude less angular momentum. So he would never form a disk. So depending on the models, I either form a disk or do not. And this is where observations come in. And the most recent observations placing constraints on the angular momentum are the black hole binary observations that we've got with gravitational waves. So we have a set of systems where they measure the chi effective, which unfortunately is not the spin of the black hole. It's a combination of the spins of the 2 black holes and their alignments. But it gives us an idea of what the spin of the black holes are. And Chris Pruzhinskaya studied populations where he tried different models. He tried the Menet models. He tried the Hager models. He tried Jim Fuller's models. And he asked the question, how well do I fit the data? And this is one of the better fits. This is using the Hager models, so some dynamo coupling. And it seems to be relatively consistent with the data. If he added some binary interactions, he could get faster spinning models. But the low spins that we see in the gravitational wave observations are best fit by something that has some coupling. The Menet models could not fit the current data. So we didn't really think the Menet models were right, but the observations proved that they were too rapid. What we really need now is more systems, more data to see if we can constrain the spins further and see whether the Fuller models are better, or Jim Fuller's models are better, or the Hager models are better. But it's at that level of there has to be some coupling. And that coupling is enough to make it so that we don't get that many disks. So spinning accretion disks, these spinning stars could explain some rare events like hypernova, gamma ray bursts, but they do not explain your normal supernova because there's not enough stars that have the accretion, have these angular momentum to make these rapidly spinning events. So data actually constrained it. It said between these 2 models, we don't have the angular momentum to have the jet-driven model explain most supernova. So I want to spend the rest of my time talking about the core collapse engine that most of the modelers have been focusing on. You have this core, it collapses. This is the inside of that core. It's a slice of a 3D simulation. In the very center is the proto-neutron star. The bounce shock has moved out and then stalled, and that gives the definition of the accretion shock. So the colors here are entropy. The arrows denote the velocity. So the core has collapsed in on itself. It's bounced. the bounce shock is stalled, the rest of the star is falling in on it. And it's piling up in an accretion shock. And the region between the protoneutron star and the stalled shock is convectively unstable. And so this is the model that we've been working on, is understanding this convection, trying to model it. This is what all the major groups have been working on now to try to understand and get simulations of. And what I want to do is say, look and see, can we constrain this engine with the observations? So one of the constraints was that when we looked at this engine, and this was quite a while ago in 1999, we said, we have this engine, it works, but it only works for stars less than about 20, 25 solar masses. Beyond that, the infalling star is too dense and the engine isn't efficient enough and it's hard to drive explosions. In addition, the potential energy, the potential energy is too high. So this is the x-axis is the progenitor mass, the y-axis is the energy. The blue curves are what we're predicting from explosion from the engine that we have. And so the uncertainty is big, but it's even with that big uncertainty, this is what we expect from the models. The green curve is the potential energy. This is what we have to overcome to drive an explosion. And so there was an expectation that we could not drive a strong supernova explosion above about 20, 25 solar masses. At the time, observations from light curves said that no, there is a paper by Myra Helmway saying, no, the supernova we see all have masses above 20 solar masses. And so they were saying the engine models were wrong. In the meantime, in the last 20 years, we figured out what was wrong with that observation. And we also got more data on observations of the progenitors themselves, found that the observations actually confirmed this prediction of the convective model. So this was a prediction of the convective model that got supported by observations. But what we'd really like is some kind of, this is a movie of those convective lobes, the outflows, in this convective model, and it starts to expand, and that's the explosion. And so this convective model predicts that the supernova engine should be asymmetric, should have blobs of material moving out. And so what we'd really like to see is there any data that can constrain that model? And so here's the theory models gone further out, where we try to calculate all the way to a supernova remnant. And the colored image here is of the titanium ejected, and it's produced right down near the engine. It's the titanium produced in the supernova explosion. Studies of this models have really changed our view on how do we interpret the supernova explosions. A lot of models before this, they focused on 1D explosions and in calculating things like yields. And the 1D explosions led to, I think, a lack of understanding of the full breadth of what we can produce when we look at a three-dimensional supernova explosion. So one of the problems with the 1D models is they struggled to produce enough titanium to explain what we saw in supernova 1987A and in the Cassiopeia A supernova remnant. And part of that is because they had poor trajectories. And by trajectory, I mean the evolution, the material is getting ejected. And if I look at a parcel of material, it has a temperature that evolves with time. And they had simple trajectories that could fit by either an exponential or a power law. And that was what they used to, make things like nucleosynthetic yields. However, when we do these multidimensional models, we see that the trajectories the material can pile up as it gets ejected and reheat. And that then changes the yields. And we can easily produce a lot of titanium just by realizing that the explosion is not symmetric. It has these asymmetries to it. But the real clincher has been, do we see evidence of these asymmetries in the supernova remnants? And this is where the NuSTAR satellite changed our whole picture. So before NuSTAR, we had the picture of Cas A, and it was mostly the green and the red image. The red is iron, the green is silicon. There was arguments that maybe this was a jet, but then NuSTAR got us the titanium-44. So The silicon and the iron, when you observe it, it's the shocked silicon and iron. We see it because the material is hot. The titanium we see through the decay of titanium down to scandium, and then so it's the radioactive decay of titanium until it gets to a stable isotope, and so we're seeing all of the titanium, and what we ended up seeing in CAS-A was a lot of clumps of titanium, and if we looked at it, we got this is a spectra of that material in the box. It shows you the titanium decay lines. So we really have a nice strong signal of what it looks like. This is from Brian Greffenstat. And these clumps tell us that whatever the explosion was, it was not a jet. It was clumpy. It looks like the engine that we have been proposing. So this convective engine. And I think with that kind of data, we really do, there's very few people that doubt that this is the engine that drives supernova explosions for these standard supernova explosions. So that does not say that there's other engines exist. That does not say that the jet engine doesn't exist. It just for Cassiopeia-A, this was not a jet engine. And I think for a lot of our normal supernova, this is probably the right mechanism.
5 minutes.
So with those 5 minutes, I wanted to leave time for questions. So I just wanted to run through my conclusions, and then I'll open up for questions. There's a lot of ideas for explaining astrophysical transients, but what you have to do when you're looking at these ideas is you have to apply both the T.H. White constraint. So if we can't rule out a model physically, it probably exists in nature, but also Occam's razor. And so in the case for a normal supernova, getting the angular momentum for jet-driven explosions is fairly difficult. So it's ruled out as a model for all, most supernova. That does not rule it out for a weird supernova. The other way to see it is if you can make predictions with your model, and then have them shown by observations, and in this case, things like what was the progenitor mass and what's the how clumpy is the ejecta, the convective engine has fit fairly well. That actually makes pushes it up to a leading model, and it's sufficient to explain a lot of the properties we see in supernova. As you move on to other transients, you'll have to look for different models. What I'm excited about with Luca's talk next is that one of the key issues for gamma ray bursts and the supernovae associated with gamma ray bursts is that a lot of them, and Luca will hopefully update my picture on this, but a lot of them are 1C supernova. And the fact that so many are 1C means that you have to look for a different engine because this is one that is not explained by the simple convective engine alone. So this is how this is a good example of how science can go, where you say, I'm trying to explain this, what are the properties, what can I explain with this model? And with that, I'll end.
Thank you very much, Chris, for the beautiful talk. And we have a question by Felix Mirabel. Can you account for a black hole formation with a mass larger than 80 solar masses, as that of the LIGO Virgo by direct collapse of a star of up to 100 solar masses?
So the problem is the progenitor models, and this is Stan Woosley's models, but lots of people have confirmed it. There's that pair instability that can occur in stellar models at around, if I look at helium cores, it's for hydrogen stars between 130 and 300 solar masses. It's for helium cores that are around 60 to 100 solar mass, 120 solar masses. Those helium cores will undergo an instability where you'll get some pair production that will actually reduces the pressure, causes the star to collapse, and it does a slight runaway collapse until of nuclear burning turns around the collapse and causes a huge explosion called Instability supernova. The problem with this 80 solar mass black hole is that's right in the mass range where we expect this Instability to exist. So we don't, I mean, core collapse could do it. If you could get a star that was, 80 solar masses that collapse, it would collapse into a black hole of 80 solar masses. It's hard to do it when the progenitor modelers can't make it. The only way you could do it with a normal, just a single star evolving is if it were rotating so rapidly that it was actually 150 solar mass helium core when it collapsed, and then you produced a disk and drove a jet that then ejected all but 80 solar masses of the black hole. I think that's a really hard, I'm not sure that's going to work, but that would be what you'd have to invoke, unless you want to invoke some of the many other models that people have been looking at, where it was formed in a cluster, where it was formed from collisions of stars. It could be formed in an accretion disk. And then we had a talk in this meeting where perhaps you can have some dark matter that changes the evolution of the star. It was dark matter. These talks have been early in the morning for me, so I only get, I'm only partially awake in them. So there, I think we may have to invoke something different to explain that 80 solar mass black hole.
Thank you. Okay, what is the mass range of the collapsing iron core in your simulation?
So most of these stellar models, the cores are between 1.5 and 2 solar masses, the iron cores. The 1.5 ones are more likely to make supernova. As you get up to the more massive iron cores, it's hard to make them explode and they form black holes. So we're slightly above the Chandrasekhar limit because they're pretty hot. So the thermal energy makes it so you can make higher than a Chandrasekhar limit iron core.
While we are identifying the supernova in generating 4 GRB in the first 2 seconds of the GRB data, 16:05:09, 16:06:25, 18:07:28, and 19:01:14. We will send you the analysis, the spectral feature, and would like very much to have your feedback. Thank you so much for the beautiful lecture.
Thanks a lot.
Let's see the next Luca. Good
Hello.
to see you. And let's start right away.
Okay, can you see my screen?
Yes.
Okay, so good afternoon to everyone. It's a very big pleasure very big pleasure for me to attend and give a talk to this unfortunately remote meeting. As already anticipated by Chris, I'm going to present some recent results that we have obtained on the class of type 1c broad-lined supernovae connected with gamma-ray bars and also not connected with gamma-ray bars. I will show some slides that maybe you are interested in. And these results are mostly observational, but they are also supported by some theoretical simulation explaining what Chris also mentioned, the role of the jet and the mixing in this type of supernova. Okay, at this meeting, we already had several talks about gamma-ray bars, physics, and phenomenology. So I want just to mention the most important property, an important property of gamma-ray bars is that their evolution of the emission, that from the prompt emission observed in hard X-ray, which is very variable and irregular, we move with time to a mostly homogeneous emission, the soft X-rays, which can be very well described by a power law decay with time. And also in the optical, since the bulk of the peak of the synchrotron emission moved from the X-ray to longer wavelengths, the optical emission also is a mirror of the power law decay that is observed in the afterglow. And this can be easily explained by the fact that the emission at these frequencies is synchrotron emission that is connected by power segments. This is an important point that I will go back later in the talk on the fact that these two emissions are connected. Indeed, if we have the capability to observe the emission from a gamma ray burst at the same epoch in different wavelengths, like for example in the X-rays, in this range, and in the optical, and if we are lucky also in the radio, we can very well constrain the emission of the GRB and eventually find additional components that can be ascribed to additional emission, like for example supernovae or other kind of emission. Well, GRBs, we know very well that they are divided in two families, that in short and long gamma ray burst. The dividing line is the duration of 2 seconds, but this classification is not only based on the duration of the burst, it's also reflected in the spectrum, in the spectrum emitted by these events in the gamma ray range. And this dichotomy led to the proposal of two different progenitors for gamma ray bursts. We will concentrate in this talk mainly on long gamma ray bursts that are ascribed to the collapse of a massive star, compact, the relatively compact star, whose collapse will lead to the formation of a black hole. And this black hole, thanks to the presence of a rapidly rotating black hole, to the presence of the accretion disk, is leading a collimated emission, giving rise to the GRB emission. Now, the energy released in this class of gamma ray bar, long gamma ray bars, is of the order of 10 to the 51, 53 Hz. And we know that is a collimated emission by theoretical consideration. And it is interesting to note that the energy released in this explosion is very similar to the total kinetic energy emitted in a core collapse supernova explosion, in particular in supernovae, in relativistic supernova, which is of the order of 10 to the 52 Hz. Moreover, another observational evidence, which is very important for long gamma ray bursts, is that they are observed very close to the brightest regions that are mainly H2 region of their host. H2 region are very massive gaseous regions in star-forming galaxy where newly stars are formed. This means that since GRB are observed very close to these regions, they die. The progenitor star leading to GRB explode, have a very low age, and then they explode very close to the region where they formed. This evidence was, for example, demonstrated in a paper on 2006 by Andy Fruchter that imaged with the Hubble Space Telescope the location of several long GRB detected at the epoch, and you can see that many of them are very close to the brightest region of their host galaxies. And indeed, during the golden age of GRB, when people started to observe intensively gamma ray burst, we were very lucky that we got the detection of the closest GRB ever observed, which is very famous 980425, the closest GRB at a distance of 40 megaparsecs. And unlike the bulk of cosmological gamma ray bursts, it is characterized by a low luminosity emitted in the prompt gamma ray energy. But since it was very close, this gamma ray burst was very close, astronomers continued to observe the afterglow of this GRB, and after a few days, they discovered the rising in the optical wavelength of an additional emission, and optical spectra revealed that this additional emission was indeed described by the spectrum of a type Icbroad-lined supernova. Just a slide summarizing the zoo of core collapse supernovae, not the entire zoo, because now with time additional subclasses are being added to this classification. According to the properties of the progenitor star, in particular, if the progenitor are stripped by the external layer of hydrogen and helium, we have different properties in the spectra of supernova. particular for the case of stripped envelope, where stripped from the hydrogen and the helium layers, we have that this star will end their life as type 1c supernova. In type 1c supernova, we do not have indeed the evidence of helium and neither the hydrogen lines, which, however, are observed in type 1b and type 2 supernovae. In particular, the class of type 1c supernovae can be split in two subclasses, the normal type 1c and the broad-line 1c. The main difference of these two subclasses is the fact that the absorption line observed in the spectrum are broad in the broad line, where the broadness can be quantified in a dozen of kilometers per second. So this means that the ejecta is traveling at almost subrelativistic speeds. Well, after 1924-25, the astronomers started to search for other supernovae connected with gamma ray bursts, and the other spectroscopically discovered GRB was detected only 5 years after the canonical case of 1924-25. And this is the case of the supernova 2003 DH connected with 030329. This GRB, unlike 1924-25, was a cosmological GRB in the sense of the total energy emitted, 10 to the 53 erg. But it was quite close. For GRB people, redshift of 0.17 is very close, a very close astrophysical source, while for other astronomers, it's still a very far event. Anyway, the fact that the total luminosity of this GRB was very high, 10 to 53, I remember, this meant that the accompanying afterglow in X-ray was equally bright, and as well as in the optical wavelength. So the supernova was overshined by the optical afterglow of the GRB. And in order to highlight the presence of the underlying supernova, it was necessary to subtract the contribution of the afterglow from the observed of the X-ray afterglow, from the observed optical emission. So from the observed X-ray afterglow, astronomers extrapolated using the power law model for the synchrotron emission, the contribution of the afterglow at the optical wavelength. And after this operation, it emerged the presence of a supernova. An additional component was a spectral feature were very similar to the supernova 98BH connected with 980425. Another GRB supernova that I want to mention is 060218. This was this is the third closest GRB ever observed, and another low luminous gamma ray burst. And as you can see in this plot, the spectrum observed from this supernova was very similar to the one of 98BW. This supernova connected with 980425. However, since this GRB was observed with the currently operating SWIFT detector, I want to remember that SWIFT has the capability to repoint the location where a GRB was detected in a few minutes, in 1 or 2 minutes, so that we can have a direct information of the X-ray and as well of the ultraviolet and optical emission from this gamma ray burst. And SWIFT discovered the presence of a soft thermal component, which was slowly rising in emission during the first 3,000 of seconds and then decayed quite rapidly in the following 10,000 seconds. This thermal component observed in the soft X-ray emission then peaked, moved, the bulk of the emission moved to the ultraviolet and optical wavelengths, and then completely disappearing after a couple of days. This emission was interpreted at the epoch as the emission of the shock breakout. So as Chris mentioned before, when we have this bounce during the core collapse, the bounce on the core of the newly formed neutron star, we have the formation of a shock wave that is propagating through the layer of the supernova, and when it reaches the photosphere, it starts to promptly accelerating and emitting a flash of thermal radiation, because in the meantime the shock has thermalized during its way to the photosphere. And this flash of ultraviolet, of soft X-ray and ultraviolet emission is capable to also produce an emission that is visible in the following few hours after the collapse of the supernova. And this is what we have observed in the case of 060218. However, in long gamma ray burst, since we have the presence of a jet, because we observed gamma ray emission produced by this collimated component, we have the formation of a jet that propagates within the stellar atmosphere, since the jet is formed by the central engine, the inner central engine, the newly formed black hole. And as the jet propagates within the stellar atmosphere of its progenitor star, it can create a sort of cocoon material, which is composed by two components, a shocked jet and a shocked stellar component that start to spread laterally after the cocoon breaks out from its photosphere. Another important property is that the jet, which forms, remember, in the very inner region of the core of the progenitor star, can deposit a considerable quantity of energy into the cocoon, which is a fraction of the total energy of the accompanying and emerging supernova. This means that, we already mentioned the fact that cocoon is characterized by a mixing of stellar and jet components. This means that we should, in principle, detect this component as the jet breaks out from the photosphere. In this video, I want to show a simulation made by the group of Hildnakar et al. Of the formation of a cocoon. So we have the jet that is formed by the central engine that continues to feed the jet by energy, and as the jet reaches the photosphere of the star, we have this additional component, the cocoon, that starts to spread laterally and can be observed in the very first thousands, if very few hours after the breakout of the jet. So another important ingredient of the formation of the jet that is continuously fed by the central black hole is that we need some important ingredient for the progenitor of this GRB supernova. We need fast rotating high iron core that can be, is not very easy to be obtained, as Chris mentioned before, but for striped embed of supernova, where we have a loss of external layers. And if the progenitor star is characterized by a low metallicity, because high metallicity is if the progenitor star is very rich in metals, it can affect the loss of angular momentum and could lead to a non-highly rotating black hole, and particularly less massive black hole. We have that we need all these ingredients in order to form a jet and possibly a cocoon in gamma ray bursts. But how we can observe a cocoon in GRB supernova? Well, generally, the main belief is that we observe a bright GRB when we are just along the line of sight of the jet. But what happens if we are just a bit offset with respect to the line of sight? Well, in principle, well, this is another slide showing that if we are just a bit offset with respect to the jet, we should observe a faint GRB due to the fact that we are offset from the long line of sight, and a promptly decaying ultraviolet and optical emission from the cocoon. There is also another case that I will mention later of the shocked jet, which I will not describe now. And in order to identify correctly the cocoon, we need then to identify immediately after the discovery of a gamma ray burst an early thermal component which cooled from the X-ray to the ultraviolet and optical wavelength. This component should have signature of the presence of superrelativistic shocked material of the order of 0.1, 0.3 times the speed of light, because the jet is bringing elements directly from the inner region of the core. And this also means that we should observe a significant level of mixing. We should observe heavier elements in this cocoon component at a very high velocity in order to identify its nature. Okay, and we believe that we are pretty sure that we have observed all these components in this GRB 171205. This is the fourth GRB, the fourth closest GRB ever observed with RSG of 0.036, and also this GRB is characterized is a low luminosity gamma ray bar, so the order of 10 to 49 erg, like 06, 0218, and 98 of 425. Looking at the X-ray afterglow emission, we have that the luminosity of the X-ray was generally lower than the average afterglow of other long gamma ray bars, and this is reflected by the fact that the GRB was not very energetic. This characteristic was very important because equally the optical emission of the afterglow was equally lower. And this led us to, this GRB actually was the best case to investigate for the presence of additional component of this cocoon emission. And indeed, as you can see in this plot, while the black point corresponds to the X-ray afterglow, the optical data show a completely different behavior. Particularly, we saw an anomalous color evolution in the first 2 days. And since we had a very good multi-wavelength coverage from the X-ray by Swift and the optical and UV from the VLT and data telescope, we have built several spectral energy distribution in 6 epochs during the first 2 days of the emission. And with this spectral energy distribution, we found the presence of a bump in the spectra of these 6 epochs that was best modeled with a thermal component. This bump, this thermal component, cooled within the first 2 days after the GRB emission, moving from temperature of 10 to the 5 Kelvin to 10 to the 4, and a radius of from 10 to the 12, in particular for the first spectrum that was obtained 1 hour, just 1 hour after the GRB detection, up to 10 to the 15 centimeter after 2 days of the GRB. So the first component, the first ingredient for identifying a Jet-Cocoon was found in the presence of a cooling thermal component, but the main results came from the optical spectra. We got very good spectra from the Gran Tecan telescope, the 10-meter telescope located in La Palma. And what we have found was the presence of this very broad bump that we have explained, thanks also to the support of spectral synthesis simulation, in this case, to the very high velocity of the order of 100,000 kilometers per second associated with the calcium ionized line. In particular, I mentioned before the TARDIS code that we use for the spectral synthesis and analysis of the supernova. Generally, TARDIS assume few inputs, like, for example, the density distribution of the ejecta. And usually people in the past, in order to model type Icbroad-lined associated with supernova, people use the CO138 model that is characterized by power law behavior. In order to fit, in particular, the early epochs of the supernova, we needed to include an enhancement in density at velocity larger than 50,000 kilometers per second, an enhancement that was also characterized by enrichment in iron peak elements. And this modification was needed in order to fit and model the early spectra of the cocoon. So after the thermal component, we had also the presence of very high velocity of the order of 0.1, 0.2 times the speed of light. We also found an enhancement in iron peak elements at the highest velocity. We claimed, we were pretty sure that what we have observed in these gamma ray bars was indeed the cocoon associated with the jet emission in 1712-05. And in this plot, it is shown the stars denotes the minimum of the absorption velocity for the silicon, on the right and the calcium ionized on the left.
5 minutes.
Okay, yeah, thank you. Well, the gray dashed line corresponds to theoretical expectation using only the CO138 model. And okay, this is plot shows the velocity evolution of the absorption line as compared to other GRB supernovae. So after the detection of the cocoon in 171205, we started a search in other recent GRB supernova, and we found, for example, we are still working on this case on 16, 12, 19b, the presence of a bump observed in the first 3-4 days after the GRB detection. The same thing on the GRB that Professor Ruffini mentioned before, 1908-29A, where there is a bump around 2-3 days. It's not very clear in this plot, but I do not have the data. I just asked a plot to Jan Bolm, and he gave me this plot. There is a bump around 2-3 days in the that observed in the optical. But what I want to say just before the end of the talk is another case, is the case of a supernova that was not connected with the gamma ray burst, for which we have found evidence of an off-axis jet and of a cocoon. So this supernova was detected in February this year, and we got a spectrum from the Asiago showing that it is a broad-line supernova by comparing with other 1C broad-line associated with the GRBs. And this plot, you can see the light curve of the supernova. It was detected by the Asensin survey, and as you can see, the behavior show a early decline in the first couple of days, followed by the rebrightening due to the supernova. We got, well, not we have analyzed the public spectra that were obtained at day 1 and day 3, and these spectra show the presence of high velocity component of the order of 70,000 kilometers per second in the day 1.5 that decay to 35,000 kilometers per second on day 4. Associated to ionized calcium and iron, while the silicon in the first spectrum was not very clear. The same was observed in 171205. Another important property of this supernova is that it was detected in X-ray and radio, but only after a few days from the supernova discovery. Indeed, coming back to the plot of the light curve of this supernova, the black data corresponds to the Swift and Chandra X-ray observation. And the first observation made by Swift on day 1 and 2 report only upper limit, while we had a rebrightening, a clear detection only after 3 days from the supernova detection. So what does it mean? We started to believe that, okay, maybe this could be the first case of an off-axis afterglow. An off-axis afterglow, and we started to analyze the different data that we have. We actually we used radio, X-ray, and in this case optical, but contaminated by the supernova, and we found that the radio and X-ray spectrum and distribution can be modeled as an afterglow in the slow cooling regime. Okay, there is possibly this is something that we are working on, a possible cocoon contribution. So, and this plot on the left shows our final results that modeling the X-ray emission as an off-axis X-ray afterglow, where the off-axis angle is of the order of 20-25 degrees, we were capable also to estimate the condition of the circumstellar medium surrounding the bars. And the blue dashed line corresponds to our best fit that takes into account also the upper limit reported by Swift and the following detection in the X-rays. So this means that for the case of this gamma ray burst, there was a GRB that we missed because the jet did not point to the Earth. And we also missed the shocked jet cocoon material, because otherwise we should have observed an X-ray emission immediately after detection of the supernova. So our location with respect to the jet was of the order of 25 degrees in the range where we have observed the shocked stellar material, which is rich indeed in heavier elements. Okay, I think that my time is over. I can go directly to the conclusion, but just if I have a few minutes, I want just to say that, sorry.
Okay, go on.
In the range of the Cork-Collapse supernovae, the class of 1C broad-line, the supernovae that are connected with gamma ray burst, correspond only to the 1% of the total number of Cork-Collapse supernovae that are observed. And of this 1%, only the 20% of this small fraction are actually supernova associated with a gamma ray burst. So what does it mean? That probably not all 1C broad-line supernovae are really associated with a GRB. So there is no relativistic jet emission. while for 2020 BVC we detected an X-ray emission and we demonstrated that there was an off-axis afterglow, the same was not verified for other supernovae. So coming back to this plot that I shown for the case of 060218, while these two supernovae, 98BW and 2006 AJ, were associated with the gamma ray bars, the other two were not associated with gamma ray bars. And in 97 we had the Beppo-Sachs, and in 2002 we had Bazzi, probably also Beppo-Sachs that were observing. And you can see that the similarities in the spectra are very striking, with the velocity of 25,000 kilometers per second of the minimum of the absorption lines. In 2006, Alisa Soderberg made a survey in the radio that the survey was, the main goal of the survey was to find radio afterglow, radio GRB afterglow in sample of 1C-Broad-lined supernova. She didn't find any signature of afterglow in a sample of a dozen of 1C-Broad-lined supernova. And very recently, also in the very nearby case of 2014 AD, the author did not find, Marco Maronjo et al. Did not find any signature of a jet, but he concluded that it could not be excluded the presence of an arrow jet offset by 30 degrees. This means that, just another couple of minutes, that since in the class of 1C-Broad-lined supernova, a real excess at high velocity was observed in absorption lines, in a paper by Fipiran in 2017. This could suggest that in 1C-Broad-lined that are not associated to a GRB, we have that the jet is not capable to escape the progenitor star because the central edging cannot feed the jet with enough energy. And we have still the formation of the cocoon because the jet is initially formed, and the cocoon, unlike the jet, is still forming. We have it can propagate in the stellar environment and then break out. This is another simulation of Pira where we have a jet that is formed by the central engine, but at a certain time the central engine stops to feed the jet. The jet dies inside the progenitor star, while the cocoon can still continue to propagate until it reaches the photosphere and then emit an emission similar to a shock breakout. And then we have the typical aspherical emission expected in the cocoon. So my summary is that jets, as also Chris mentioned in his talk, can play a fundamental role in this particular subclass of core collapse supernovae. Sorry? Sorry? Okay, just to mention that we have found evidences of this jetted component through the detection of cocoon emission in the GRB supernova 171205. And also, well, we have found the first off-axis afterglow that was discovered thanks to its accompanying supernova 1C-Broad-lined. This is all for my talk, and questions are very welcome. Thanks a lot for the attention.
Thank you very much, Luca. We have Maria Pruzhinskaya.
Yes.
In your opinion, should all long GRB be accompanied with supernova, but we do not usually observe supernova due to its faintness or not?
Well, long GRB, in my opinion, are all accompanied by a supernova because they formed from the collapse of a massive star, so we should observe a supernova. There are a couple of cases of long GRB, peculiar long GRB, observed both in 2006 that were also close GRB, but we didn't find any supernova underlying their emission. But people are reinterpreting this GRB in a different context that I don't want to discuss here. But yes, in my opinion, all long GRB are accompanied by 1C-Broad-lined supernovae.
Thanks from Maria Pruzhinskaya, and thanks for all of us. We can then proceed to the next talk of Jorge Rueda. Okay, Jorge, you can start.
Okay, good afternoon to everyone. So I'm just trying to minimize this the panels from my screen just to see better my presentation. Sorry for that. Okay, so thank you for inviting me to present this talk. So this is an update of the binary-driven hypernova scenario. This is a work. This is let's say a collection of not only a summary. I will present some new results, but first I will summarize. And this is a work in collaboration with many people, which I would like to thank. First, going ahead with the slides. So this is a big collaboration with people from everywhere in the world, and some part of this part of this work has been made in collaboration also with the group of Los Alamos, led by Chris Fryer. So I will mention the specific points of this collaboration. So this, let me start. So of course I can. So I can skip some details of GRB. So binary-driven hypernova scenario is a model for the explanation of long gamma ray bursts. Essentially, but not only. As you see in the left side of the slide, actually, we have a common evolutionary scenario for the explanation of both short GRBs and long GRBs. Differently from a typical, let's say, traditional model of gamma ray bursts, of long gamma ray bursts, which is based on single channel explanation. So based on the collapse of single star in the binary-driven hypernova scenario, as the name says, is based on binary. What is this binary? So the binary that produced that, actually the long gamma ray burst, this action takes at the final stage of evolution of a binary system, in which you have the supernova explosion. You have a binary here. This is exploding stars, or an evolved star exploding a supernova. That's the 1C supernova in presence of a neutron star companion. And in this process, this neutron star is nearby to the supernova, and is so near that actually it can accrete a lot of material from the supernova explosion, and eventually this neutron star can, by accreting this material, can collapse to a black hole, or actually can become just a more massive neutron star. And this gives the variety of a scenario. So actually, the binary-driven supernova in which the neutron star collapses to a black hole, we call them of type 1. With the other one, we call of type 2. So in which the neutron star doesn't get enough mass to collapse to a black hole. So we have this scenario after after the explosion and after the collapse or not of the neutron star companion, you form a new binary. In due time, this binary will merge and eventually form a short GRB. So this is why this is a common scenario for both formation of long. Here's a long GRB, and after the remnant of this GRB, let's say the remnant system of this long GRB will eventually produce a short GRB. I will concentrate in this talk only on the long GRB emission. So on this process on the right side, so the explosion of the supernova, the accretion of the neutron star, and all the observables of this process. So this starts with a series of work. So based on this, we started to make simulations of these kind of systems to show actually this may actually to happen. So the first simulation was in 2014. We started to collaboration with the group of Chris Fryer. We first tested, let's say, this idea of verified by numerical simulation. Somehow, let's say simpler with respect to the one what I'm showing you in a moment. This is only one-dimensional simulation of an explosion of a supernova, and then we show that actually in few seconds hundreds of seconds, in a fraction of hundreds of seconds, the neutron star can get enough mass to collapse to a black hole, so can reach critical mass for gravitational collapse. But we didn't, in these simulations, we didn't follow the evolution of the neutron star and the Kilin neutron star. So this was our first simulation. Then we went to a different simulation the year after, 2015, including the effect of angular momentum. And then, but it was a two-dimensional simulation. And then I moved to the three-dimensional simulation that was recently, last year, in which we were combining a two-step calculation. So first we simulate the supernova in presence of the neutron star companion, and we evolve the matter of the supernova, which the supernova expanding material, and how it accretes into the neutron star, and calculate first which is the rate at which mass is falling to the gravitational region of the neutron star. And then we compute from this calculation, we can evolve the neutron star structure, so we can know how evolved the gravitational mass of the neutron star, and also the rotation of the neutron star. But not only in these simulations, we also evolve. Maybe you recall you remember from the talk of Chris Fryer. Sorry for the talk of Chris Fryer. These are also the fallback accretion. It's not it's this fallback accretion onto the neutron star, which is forming at the center of the supernova. So actually, in this simulation, we follow all the two accretion processes, so both on the neutron star companion and on the neutron star at the center of the supernova, which we call the new neutron stars, the newly formed neutron star. So there are two accretion processes. In the two accretion processes, there is an important component which I didn't mention at the beginning, but I must do it. Actually, this accretion process, the rate of accretion I will show in a moment, is very high, and actually I show already here. It can be of the even of the order of 10 to minus 2 solar masses per second. So a fraction of solar mass in a second. So it's a huge accretion rate of the neutron star companion, and this is allowed by the presence of a strong flux of neutrino and antineutrino emission going from the neutron star close to the neutron star surface. So again, in this new three-dimensional simulation, this is an initial condition. This is a supernova explosion and the neutron star companion. This is from the supernova code of Los Alamos. We simulate the explosion of the supernova, and then we follow. And when we follow, this is here. You see the explosion in presence. This is the neutron star companion in a tight orbit of the order of 5 minutes orbital period. And you see the accreting material. This is the density plot. So you can see the accreting material forming a sort of vortex around the neutron star. So this is a sort of accretion disk. And then we can simulate. And here is the formation of the new neutron star. You see this blue region here. So you see the formation of the new binary. Here, then we can construct the evolution of the neutron star accreting this matter and know how the mass is evolving, how it's increasing, and determine the point of gravitational collapse. So this is, of course, we can also evolve other additional quantities, thermodynamical variables. This is, for example, the evolution of the temperature. So you can see this little bit of accumulation with higher resolution. Again, you have here the supernova explosion, and here the neutron star. So we can reconstruct actually the history of this process, and everything happens just in few seconds. This is an important point. Then, just to show you a summary of some quantities of some important things of this system. So these are just snapshots of the simulation, and this is the what I mentioned before. But around the neutron star, you have this matter going around a sort of accretion disk. This is actually the angular velocity. So it's angular velocity of the material around the neutron star companion during the accretion process, which actually almost shows almost a Keplerian behavior of this circularizing matter. So you can see also here, this is velocity field in this process, you can see very well the rotation here of the matter around. Here is that was a orbital plane view, and this is a polar view. So it's the view from the top, where you can appreciate also this structure of neutron star and how the region. You can see the deformation actually. Also here you can see the deformation of the supernova ejecta due to the presence of these companions. So it's not anymore a spherical. The star is spherical, but it's got very deformed, causing what we call a cavity around the neutron star companion, which becomes a black hole. So these are some numbers of the accretion rate. So this is accretion rate onto the neutron star companion, and this is accretion rate onto the new neutron star, so the one formed at the center of the supernova. So it can be pretty high in the accretion rate. And after, with this knowledge, of course, we have to simulate the neutron star evolution. These are some numbers of the neutrino emission. So can have temperature, the rate of electron positron annihilation creating the neutrino emission, and some other numbers that are interesting for the study of neutrino emission related to this process. For example, we study here in this work. So then jump this. Of course, you have the equation of the state of the neutron star, the equation of the structure, and the equation for the evolution. So how to evolve the gravity, how to know the relation between the gravitational mass and the rest mass of the neutron star. So to know for a given accretion rate of ionic matter, what is the change in the gravitational mass of the neutron star? So you have to know that. The only way to know that is to construct the structure of the star. For at any time step, you have to evolve the mass and the angular momentum of the star. So, for example, this is evolution of the neutron star in the mass in the stability plane. So mass, the central density plane. So it starts, for example, here, and by accretion it can go different evolution depending on the initial conditions of the system. At the end, it can reach here. This is specular symmetric instability line, and this is the line for the gravitational collapse. So this is the Keplerian mass shedding limit. It's this one. So we can establish in which instability line the neutron star is reached, and in how much. So how long it takes the neutron star to do that? Because the idea is, as you have just listened from the talk of Luca, so we have these long GRBs that are associated with supernova. So we see and the supernova, but we also see the prone GRB emission, gamma radiation, which we associate with the formation of the black hole. So we have these different processes which depend on the different physical ingredients of our binary. So all this for us is important. So also the time in which the collapse occurs is important in this picture. So this is again, this is just a summary of the evolution of the instability regions. Also, we can of course demonstrate that actually a binary-driven hypernova form a neutron star black hole. A binary PDA-SN of type 1 actually form a neutron star black hole binary. This was shown in no simulation. It means that actually the binary is not disrupted by this process, but it keeps bound, and so the neutron star black hole binary survives to this process. Let's speak about some astrophysical observables in the, let's say, low energy rotation max for GRB, so less than GeV energy. So for important is the three-dimensional picture, so three-dimensional morphology of the PDA-SN. So this can lead to different a variety of observables, because then now it depends if you are looking at the GRB from the top or from the equatorial plane, so from the orbital plane, it leads to different things. So, for example, let's just quote some of the works from our group related to the appearance of X-ray flares in the afterglow or in the early afterglow of the GRBs, the existence of gamma ray flares, in the transition from supernova from hypernovae, and also from the different observables from the how to determine if we are looking at a source from the orbital or from the polar plane. So this is with a higher resolution, the three-dimensional structure of our system. So you have to see the system here around. Here is the neutron star accreting. This is not yet at the moment of black hole formation, just to show you this how the morphology of the matter around the stars has been changed by this process. What happened is that depending on that around the neutron star there is this cavity, and there is this material is not anymore homogeneous. So depending on the line of sight, you will have less or more matter. So it can lead to different let's say amounts of baryonic matter. If there is, for example, the formation of an electron-positron plasma in the black hole formation process, then this plasma will travel in different. You have to travel to go through different amount of mass to after let's say breakout and after to see. That will determine if you will see if we go through an amount of baryonic matter which is small, then you will see this as a prone gamma ray radiation. Otherwise, you can see what we show. It can be also seen as an X-ray flare or a gamma ray flare. So this is exactly what I just mentioned. Depending on the different view, then you can see different components of the radiation from an electron-positron plasma forming the black hole formation process. Then you have I mentioned already type 1 and type 2 supernova. So type 1 you have the black hole formation, so you form the new neutron star black hole binary, or in type 2 you form just new more multi-neutron star companion. And you can identify identifying the two cases that this paper actually we were investigating was the X-ray afterglow, and to show that actually the presence of the afterglow, but important key ingredient of the explanation of the X-ray afterglow is the new neutron star. So you see the new neutron star is a common ingredient even in type 1 and type 2. So we actually were showing that either in type 1 or in type 2, the presence of the new neutron star is observed, making this let's say a confirmation of the VDSN picture. So this is a summary, a table of summary of different processes in physical processes at the energies lower than the GV energies. And how do we display them in this in the VDSN picture? So we have a lot of processes, and depending on each addition following the time evolution of the system. So we have the supernova evolving, what we call the explosion, the supernova, we call the supernova rise or the SN rise. Then we have accretion onto the neutron star black hole formation, and then we have electron-positron plasma formation. Then we have then the material of the supernova continues to expand, and then there is the action of the neutron star at the center, which powers the supernova ejecta and produce synchrotron radiation. The synchrotron radiation explains the afterglow of the GRB. Now there is what happened at energies lattice and GeV. So this is a process in which is involved the presence of the newly formed black hole, so the object that formed from the collapse of the neutron star. And this black hole has some matter around, has also the magnetic field, which was the magnetic field of the collapsed neutron star. So these three ingredients form what we call the inner engine of the high energy emission, which would explain the energies above the GeV. So let's say from 100 MeV, 0.1 GeV. So first concept that I would like to mention here is what we call the black hole quantum of energy. So this is the black hole quantum of energy. If you see all this model of the inner engine is based on the mathematically on the exact solution of the Papapetrou-Wald solution, which is you have a rotating black hole, so a curved black hole immersed in a magnetic field, which is asymptotically aligned with the black hole rotation axis. So from this you can calculate which is the magnetic field and the rotation of the black hole. And this is an electric field, and this electric field actually is the one which accelerates particles, the particles that are around, and in this fully ionized gas around the black hole, which is left around the black hole, it's a very low density, but particles are there and get accelerated by this machine. So this now represents some numbers of this machine. This is actually a very powerful and very efficient machine to accelerate particles. So here is the electric field, the energy gain by a particle at the from this is the complete difference of potential energy from the horizon to infinity. This can complete the electric field at the horizon as an order of magnitude of the electroaccelerating field. And then you can compute also what would be the time scale of acceleration of particles along the black hole or the black hole rotation axis. And then why we call this the black hole quantum of energy is when you compute what is the energy available to accelerate the particles, then you can write that quantity is in this way. Yes, it's as the quantum of energy, actually, which h bar times some effective frequency. This effective frequency depends on fundamental constants and on the angular momentum of the black hole and the magnetic field, which is around the in which the black hole is immersed, and of course depends on the mass of the black hole. So the same you can do for the energy, maximum energy of the particles, in which the energy gained by the particles can also be written in this way, in this very suggestive way. And there is another important point, is that this machine actually works not only for GRBs, but it works also for AGN. Actually, in our paper we show that numbers both for GRBs, taken as a proxy, GRB 15 of 47A, and for IGN, taking M87 as a proxy. So this is just few numbers along for the acceleration of particles along the black hole rotation axis. So the black hole rotation axis, there are no losses of energy, so the particles can reach the highest, the largest possible acceleration energy, and so they are along the black hole rotation axis. We expect that GRBs to be sources or to contribute to ultra high energy, to the production of ultra high energy cosmic rays. But then what happened for outside the black hole rotation axis? So outside the black hole rotation axis, so the off-axis radiation. So this off-axis radiation will produce observable high energy, so in the energy in the GeV regime. So this was shown in this paper, 2019. And so what happened is we have electrons around we have the electrons, and the electrons around the black hole get accelerated. If you have the black hole, the magnetic field aligned with the spin of the black hole, then the electric field if the electric field that is induced points downward, and some electrons are accelerated outward and moves outward to escape from this region. But if there is a magnetic field, they produce synchrotron radiation. So by synchrotron radiation, it can be shown that this combination of this inner engine and synchrotron radiation produce what you expect, what you see actually in the GeV emission of GRBs as mentioned by Fermilab from that satellite. So this is an example. This is GRB 150427A, and the red points are the emission observed by Fermilab, and this is the typical numbers for this mechanism. So we compute the large gamma factor by the electrons, the cooling time of the bisynchrotron radiation, and typical energy of photons, or the photons emitted by this mechanism. And so from this, of course, one of the most important parts that we want to when we model some observable is to have to extract the parameters of the model. So here, what is important, we would like to extract the energy parameters, which is the mass of the black hole, which is the angular momentum of the black hole, and which is the magnetic field around the black hole. So these are three quantities, and we show that actually it can be obtained by requesting just three conditions. One, that the GV energy budget comes from the black hole, so from the black hole extractable energy. Okay? And so this comes from this, it leads up to this formula. Alpha is the dimensionless angular momentum of the black hole, so J over m squared. Second, that is synchrotron radiation, which is responsible for the high energy emission. And third, and I miss here one third here, is that this actually the transparency of the high energy photons, so that actually the high energy photons can actually escape the system. In this case, one of the most important process which could avoid that is the magnetic field production. So the interaction of high energy photons with the magnetic field could produce electron-positron pairs. But in this case, we just we request that it doesn't happen, and this just impose a condition for the magnetic field. So actually, with these three conditions, you can reconstruct this plane of solution. And this is the case of GRB-1347A and GRB-190114C. What you get is exactly what you expect from the deviation model, namely that the mass of the black hole is perfectly in line with what you expect from a black hole from the collapse of a neutron star by accretion. And then for the magnetic field, you get that this is between 10 to the 10 and 10 to the 11 Gauss. This is from the this emission in the GeV regime occurs for a specific pitch angle. So that
5 minutes.
Okay, that's fine. That's fine. And this radiation comes from a specific pitch angle. Pitch angle is the angle between the electron motion and the magnetic field. So as you can see here is that actually, when this emission we have shown this that the all GeV emission comes within 60 degrees, roughly within 60 degrees from the rotation axis of the black hole, so forming a sort of conical emission of right angle. This is important for the morphology of the GeV emission region, which can be also let's say extracted from analysis from the statistics of the GeV emission of long GRBs. Then these are the, I think I have three more slides. When this is going a little bit farther, here now just finish a work which would make a more detailed treatment of the acceleration of electrons in this system. So what you see here is actually the electromagnetic field. So you see here the orange lines, these magnetic field lines and electric field lines for a specific value of the mass and angular momentum of the black hole. And you see the color background, the energy, the electric energy density, so the energy available for acceleration of particles. So you can see already this is the region of in which electrons can be accelerated. This one and this one. Then of course you have to go and integrate the equation of motion for the charged particles for this solution. So of course you can do it only numerically, but it can be done. So you can actually compute that and going ahead, and you can compute also to estimate. So once you estimate the trajectories, of course you can reconstruct the pitch angles of the electric motion, and you can obtain which would be the photon emission as observed at infinity. So this you can reconstruct the photon momentum and the photon momentum components as measured at infinity, and recover first you can recover some traditional result of the special relativistic aberration that you expect observer at infinity to observe, and but in addition you see also a component of the momentum which is dominated by the frame dragging effect. Then you can reconstruct, of course, the gamma factor and reconstruct the which is the power emitted per particle, the energy emitted, the photon energy emitted by this particle, and reconstruct the spectrum. And actually to confirm that actually you can produce high energy emission by this kind of mechanism. This is an example for four solar masses and dimensional circular momentum 0.3 and a magnetic field of 10 to the 11 Gauss, confirming all the previous results actually of the most simpler model, so much simpler model that I showed before. So actually what's important is that GeV emission seems to come from everywhere within 60 degrees from the black hole rotation axis. So conclusions. So there is no bulk expanding motion is needed for the explanation of high energy emission. The inner engine is rotating black hole surrounded by magnetic field and ionized plasma. Then the black hole rotation and magnetic field induce an electric field that accelerates the electrons, and these electrons radiate by synchrotron radiation in GeV regime and above the GeV regime. The energetics of this emission is paid by the black hole extractable energy, which is, this is the rotation, which together with the magnetic field, which induce the accelerating machine. Then the GeV emission is radiated from electron with appropriate angles, and they appear to occur within 60 degrees of the rotation axis, which is a crucial test for the morphology of VDSN. Thank you.
Thank you very much, Jorge. Beautiful talk. There is a request by Felix Mirabel. Interesting talk. Massive stars are formed in binary and multiple stellar systems. To what stellar progenitor masses this binary supernova scenario is valid?
Yeah, this is actually very, very, very interesting question. And this comes from also from all analysis of the afterglow, in which this comes together. Okay, from one side we can determine this from the request of the collapse of the neutron star, and second observable for us would be the analysis of the X-ray afterglow, which is produced from the interaction of the neutron star emission with the supernova jet. So from these two requests, we can analyze which is the amount of ejecta that we need, and which is the amount of ejecta, so which is the progenitor. So, and the very, very nice thing that seems that we obtain from this analysis is that actually all on GRB seems to be produced by very similar progenitors. So actually, we don't think that the mass of the Volt star must be in some wide range. It actually points to a very narrow range of very narrow masses, which point to progenitors for zero-age main sequence mass between 25 and 30 solar masses or something like that, about that, around that number.
Thank you very much. We have to go ahead to ValeryChechetkin. Thank you again, Jorge.
Thank you.
And let's proceed.
Yes.
Thank you.
Valery, it's a great pleasure to see you.
The next, please, slide. Okay. You may see from our slide our main result connected with the problem exist of neutrino from the central region of supernova explosion. For me, that is my opinion. I think that is the main problem for explosion supernova and for region of neutron star, because you must obtain additional energy for outflow of the supernova explosion. This energy may contain only in neutrino stream, or maybe, if you recall work with Type on to magnetic field. Because in my report beginning, I stop brief on history development of supernova, which main physical process very important for supernova explosion. For my opinion, post physical effect for supernova, that is effect of rotation pre-supernova. Second, appear large-scale instability. The next is very important problem. That is correct description of the neutrino exit. Next slide, please. That is post three-dimensional calculation involved convection instability without rotation. Next slide, please. That is development convection instability around neutron star, if you including rotation in correct exist neutrino. What is neutrino have such big role? If you recall, very old time, beginning of 20th century, for supernova, very important gravitational energy. But gravitational energy contained in the electron, because it's very important problem. Please, next slide. That is unequilibrium neutronization owing this process gravitation energy. What is mean gravitation? No gravitation. They obtain energy from gravitation. The next question we must solve, that is problem existing neutrino, because to understand around neutron star we have very much matter. In this case, it's very important problem appear large scale instability. Next slide, please. Okay. This is I stop on problem origin heavy elements. That is explosion, rotation, solar mass. You can see you obtain owing to rotation asymmetric distribution whose time asymmetric distribution. You can see distribution various elements. Next slide. That is effect development large scale instability with account rotation. This is very important for supernova type 1. Picture you may see is very close to nuclear explosion. In this case, I may say only one massive astrophysical effect which have laboratory experiment which very like on nuclear explosion. Next slide, please. Okay, if you recall, I said about very important problem description, correct description exists neutron star. The next my report continue Professor Akselov. Леша, ты здесь? Леша. Sorry. Okay, I continue. You can see the next very important Boltzmann equation for correct description exit neutrino. You must using this kinetic assumption. The next report. The next slide. You can see calculation, two-dimension assumption. During unequilibrium neutralization, energy neutron. Energy of neutrino may have a value but endurance exists to surface of supernova. This energy must lost. You recall work mechanic and Nadezhin, which calculate exit neutrino. But if you will have large scale convection, in this case, peaks of matter capture high energy neutrino very quick, lift the neutrino to transparent region. We obtain very okay. Yosha, you may continue.
Valery, still 3 minutes.
Yosha,
Valery, you have 3 minutes.
okay. Next slide. You can see calculation, entropy, calculate entropy, and entropy per nucleon, solid law, electron number, or neutralization, and adiabatic index gamma. You can see. Okay, next. You can see, one moment. You can see. Okay. Please continue. In this region, for owing to go away neutrino from result of this exist of neutrino, we obtain development the big bubble which go to surface. This bubble contain high energy neutrino which lift to surface and support kinetic energy for envelope of supernova explosion. Okay?
Okay.
Next slide, please.
Cosa è successo? Si è staccato?
No, professore. No,
It's a very important result you can see. We compare two calculations in a very similar initial condition. But you can see that is this energy for neutrino, stream neutrino for two-dimensional calculation and one-dimensional. You can see that is energy increase and almost 2 times. This
Very
energy
nice.
enough for out the way envelope of supernova.
Thank you, Valery. We are out of
Next
time
slide.
for this result. Okay. These, I presume, are the conclusions.
This our main result. Now we prepare our result for publication. What the main our result convection arrives of central region for the gas dynamic time. It is time for lift of convection bubble neutralization, which was several very important. I mean, it was certainly fraction of utility. We have energy from an equilibrium neutralization, but we have not changed, go away, change amount of neutrino. If you take many two three-dimensional calculation, the numerical calculation, supernova explosion without a count, without the count exists neutrino in this calculation, science don't obtain appear large scale convection structure because without calculation kinetic equation for neutrino distribution, you don't obtain increase entropy. But for to understand, for appear very big gradient entropy. Okay.
Thank you very much, Valery. We don't have other question, and thank you again for this very interesting talk and the role of three-dimensional, two-dimensional versus one-dimensional for the neutrino expansion. Maria Pruzhinskaya now is the next speaker.
Hello, everyone. Do you see my screen correctly?
Yes, perfect. You are Lomonosov State University and Sternberg Institute.
Right.
Two great institutions. Okay, let's go on.
Yeah, let's start. I'd like to thank the organizers, first of all, for the opportunity to give a talk on such a wonderful conference. And it was a really great pleasure to attend this meeting. I'll talk today about Type Ia Supernovae and their use for cosmology. Oops. Supernovae divided by different types and subtypes according to their spectral features and light curve shape. And Type Ia supernovae, which we basically use in cosmological analysis, stand aside from all other types. They arise from the thermonuclear explosions of white dwarfs that exceed the Chandrasekhar limit of stability mass. And during the explosion process, usually 0.6 solar masses of nickel 56 is produced, and the decay of this radioactive nickel is responsible for the light curve behavior for the luminosity of type Ia supernovae. Basically, since the amount of nickel is more or less the same all the time, the supernovae have very uniform light curves, and this amount of nickel is really a lot. So type Ia supernovae are very luminous. And these two properties actually allow two international groups of astronomers to discover the accelerating expansion of the universe. Here on the slide, you can see the Nobel Prize Hubble diagram. And according to this Hubble diagram, our universe, as you all know, accelerating with a dark, our universe is accelerating and consists of dark energy on 70%. However, this very important discovery would never be possible without another very important discovery, the discovery of the relation between type Ia supernova luminosity and their light curve shape. So basically, the light curves that are broader, or let's say where the light curve declines very slowly after the maximum light, so such supernovae will be brighter. And this was discovered in the 1970s by Soviet astronomer Yuri Pskovsky and American statistician and astronomer Bert Rust. And here on the slide, I show the original plots with this relation. And I do it because I'm really impressed by the fact that they did this discovery. They found this relation based on the data quality that they had that time. With the appearance of CCD camera, Mark Phillips re-inspected this relation and confirmed it using a beta supernova sample, and he did it with a better quality. Now, there are many other standardization procedures of type Ia supernovae. I cited here only two of them, SOL2 and one of the most recent, Sugar. And basically here in the parentheses, you can see the so-called standardization equation. This equation takes into account the dependency of supernova luminosity on the stretch. So the parameter that is responsible for the light curve shape. And it was also found that intrinsic luminosity of type Ia supernova depends on supernova color. Below you can see two figures. So one represents the light curves of different supernovae, how they are observed. And here on the right, you can see the light curves of these objects after the so-called stretch and color correction. However, even despite of this standardization, there is still remaining intrinsic luminosity dispersion of type Ia supernova on the Hubble diagram. For example, in one of the most recent cosmological analysis, it is about 0.11 magnitude. So it means that type Ia supernova are neither standard candles nor standardizable. What could be the reasons of that? First of all, it's absorption. Absorption in our galaxy and in host galaxies of supernovae. Then it's a chemical composition of progenitor system. So the further into the universe we look, the earlier in chemical sense star population we see. Then there could be several different scenarios of type Ia supernova explosions. Among the most popular are single degenerate, where the explosion is a result of matter accretion in a binary system on a white dwarf from the companion star. And the double degenerate scenario, it's a merger scenario, so merger of two white dwarfs. Then the total mass of merging white dwarfs can evolve with Hubble time. And of course, there are different observational selection effects, such as Malmquist bias, while in the nearby universe, we can observe both bright and dim objects at high redshift. Only the brightest can be detected. Oops. However, it was found and was proved in many works that Type Ia supernova luminosity depends on the environment as well. This environmental correction is known, but it is not implemented directly to the standardization equation of Type Ia supernovae, as it is done for the stretch and color parameter. So this correction roughly implemented directly to the cosmological analysis, but I would not still say that it is taken into account in the standardization procedure. We roughly divide the parameters that can characterize the environment by local and global parameters. So global parameters are the parameters that characterize the whole galaxy itself. So it could be host galaxy morphology, star formation rate, metallicity, color, and so on. And the local parameters in turn characterize the supernova environment in a very small region. Okay, not very small, it's around 1/3 kiloparsec in some region around supernova. Obviously, local parameters can better characterize the environment, and this is already proven in many works. However, with the current stage of data processing and current resolution of the largest telescopes, it's quite difficult to measure the local parameters at high redshift, or it is very time-consuming process. And of course, we cannot allow ourselves to spend a lot of time when we'll have thousands of even more millions of Type Ia supernova, for example, with run of LSST. That's why in this work, we choose host morphology, so the global parameter, to characterize the environment of Type Ia supernovae. Let's say that we divide the host galaxies of supernovae by early type galaxies, which are lenticular elliptical galaxies, and late type galaxies, so basically spiral galaxies. What is the justification of such a division? First of all, it's absorption. So it's known that in elliptical galaxies, there is no dust. However, in spiral galaxies, there are a lot. Then it's chemical composition. So again, in elliptical galaxies, we mainly have old metal poor stellar population, while in spiral galaxies, we have stars of different population. And finally, it's a mechanism of explosion. So we believe that in elliptical galaxies, the main mechanism of Type Ia supernova explosion is a double degenerate mechanism, so merger of two white dwarfs. Here on the plots, you can see the so-called delay time distribution. So here, y-axis is event rate, so how many supernova exploded per year, let's say, versus age of elliptical galaxies starting from its formation. So the blue curve here corresponds to the single degenerate scenario, and this red curve corresponds to the double degenerate scenario. Black dots are the observational rate of Type Ia supernova in elliptical galaxies of different ages. So you can see that observations fit quite well the theoretical curves that correspond to the double degenerate scenario. For the analysis, we choose one of the most recent cosmological samples up to supernova samples up to date. It's Pantheon cosmological sample that contains of 1,000 spectroscopically confirmed type Ia supernovae up to the redshift 2.3, and it's basically represent the compilation of different supernova survey, like 20 low redshift supernova surveys, the CEST, SNLS, Hubble Space Telescope supernovae, and Pan stars. To determine morphology of Pantheon supernova host galaxies, we used SIMBAT, HyperLED, and NET databases, so few astronomical databases, and some individual publications. Finally, we were able to determine morphology for 330 supernova. 91 of each belong to the early type galaxies. And here you can see the redshift stretch and color distribution for our subsample and for the whole Pantheon sample. So the selected sample is not too biased from the point of view of stretch and color parameters. However, there is a strong bias in terms of redshift. That is basically explained again by the fact that it's easier to find morphology for the nearby supernovae. Here, I present the distribution of stretch and color parameters depending on the host morphology.
2 minutes, 3 minutes.
Yeah, thanks, yes. Depending on the host morphology of supernovae. Squares are the mean values for each morphological beam. And you can see that the stretch parameter continuously increases from the elliptical to irregular galaxies. And on the right subplot, you also can see the histogram for the stretch distribution when we divide our galaxy by late type and early type only. And there is quite a prominent difference in these two distribution. And the significance of this difference is more than 8 sigma. However, if you look to the stretch, to the color parameter distribution, there is no any trend either for detailed morphology or for two-group separation. We also reproduced the Hubble diagram from the Pantheon analysis. Different markers here correspond to the supernova that belongs to different hosts with different morphology. So the dashed line is a model that correspond to the lambda CDM cosmology. And we also looked at the residuals distribution, distance modulus residual distributions on this Hubble diagram, depending on the detailed host galaxy morphology and for two groups. So it's probably not very seen that there is any tendency for the detailed morphology here, but when we divide the host galaxies by two groups, there is a small difference, and our statistical tests basically show that this difference is significant. So for the early type galaxy, the residual dispersion, the mean residuals is smaller. So it means that in elliptical galaxies, after stretch and color correction, type Ia supernovae are brighter. And let me conclude with this slide. Basically, we studied the influence of host galaxy morphology on light curve parameters and supernova luminosity for Pantheon cosmological samples. We confirmed that the stretch parameter depends on host morphology on high level of significance. However, no correlation for SOL2 color parameter is found. We also found some different in residual dispersion on the Hubble diagram for different host morphology groups. And finally, we confirm the importance of including a host galaxy parameter into standardization procedure directly for further cosmological studies. Thanks for your attention.
Thank you so much. Thank you very much. There is no question, and thank you again for the very nice.
If I may quickly, it's Gregory Vereshchagin. Just a quick question. Any physical interpretation of this difference with morphology? I mean, dust absorption or whatever physical reason for this difference?
Right. The physical interpretation is following. So it's probably metallicity. So the metallicity of progenitor stars, or it also can be some absorption, as you correctly mentioned.
Thank you. Thank you again.
Thank you.
Let's proceed again to Elena Balakina, last speaker of this intense meeting, 1 week meeting. Okay, Elena.
Good evening, dear colleagues. My name is Elena. I'm a student of Sternberg Astronomical Institute of Moscow State University. And today I would like to present to you the report investigating the influence of peculiar velocities of supernova 1A on the distance measurements and as a consequence on the evaluation of the Hubble constant. Now, you know, there are two main ways for estimation of the Hubble constant value. The first way is based on the CMB observations and give us such value. And the second one based on the supernova 1A data. This method allows us to measure the Hubble constant using the luminosity distance redshift relation. As usual, particular attention is paid to standardization of the supernova type 1A, as Masha told, and those methods leads to increasing of the accuracy of luminosity distance determination. And however, those analyses neglect the uncertainty on the redshift. And this problem is the main topic of our research. We would like to decrease the residuals on the Hubble diagram by improvement cosmological redshift measurements. On the next slide, you can see the Hubble diagram. The black solid line shows the Hubble limiter law, and the arrow presents the shift caused by the radial peculiar velocity of the supernova's host galaxy. For low redshift, we can assume that dependence of observed redshift looks like this. And the next slide, we plot using this assumption, this graph. So in our analysis, we use as a sample of supernova 1A Pantheon sample, which contains about 1,000 objects. And the great value of here, you can see that the greater value of this radial component leads to the greater value of the uncertainty on the redshift. Redshift uncertainty here recalculated in magnitude value and by this formula due to different levels of peculiar velocities as a function of a cosmological redshift. So here you can see the black solid line, which corresponds to the peculiar velocity value which used in the Pantheon sample. And these dashed and dotted lines corresponds to clusters of galaxies in nearby universe. And you can see that they're much greater than this value. And the intrinsic value of intrinsic dispersion value of the Pantheon sample, it's the two yellow lines on this graph, for different scatter models, they cannot cover this uncertainty. So we can say that these standard methods to take into account peculiar velocities do not work exactly for the nearby universe for the Z less than 0.2. That is why we assume that for supernova in clusters, it is more accurate to estimate cosmological redshift as the host cluster redshift instead of the host galaxy redshift. Clusters also have their own peculiar velocities, and for example, bullet clusters, which are example of the merging clusters. Nevertheless, clusters, as usual, have much smaller peculiar velocities than the galaxies within them. And the first step of our research was to find the reliable clusters catalogs, which based reliable means that the data based on the X-ray observations and the Sunyaev-Zeldovich effect, as they can guarantee us that the hot gas inside the cluster. And we collect the following list of catalogs. They use different data from XMM and Planck and others.
Very good.
Satellites. And yes, we found 34 supernova 1A in the clusters in the nearby universe by cross-matching these catalogs with the Pantheon sample. And all found supernova 1A are with a redshift less than 0.2. So we do not consider the supernova with a larger value of the redshift, even if they in the clusters. Just this effect is important only for nearby universe.
Thank you very much. Thank you very much for this. Okay. Oh, you have not finished yet.
Yes. Okay. Maybe the last one. On this slide, I just want to show you the first results of such kind of analysis. There was only 11 supernova 1A in clusters, and this the correction which was made has a reliable improvement of the Hubble diagram, so the residuals are decreased. And this is the main
conclusion.
Yes, conclusions. So in conclusion, I can say that unknown peculiar velocities are an additional source of uncertainty on the Hubble diagram, and we are developing a method for assuming supernova Venn clusters of galaxies and using sorry, and using the redshift instead of the host galaxy redshifts to improve measurements of the Hubble constant and other cosmological parameters. Thank you for attention.
Thank you very much. We close on this very nice presentation. Congratulations. And let's turn now, and all the people who have participated in this session. We turn now to the conclusion. Who is the conclusion? Does this result affect on H0? Oh, there is a question.
Yes.
What is the conclusion? Does this result affect on the H0 value? Or is still...
No. This research cannot change the Hubble value, but we can decrease the residuals on the Hubble diagram. So our value of the Hubble diagram, or the Hubble constant, is more accurate.
Yes. Thank you very much again.
Thanks.
We can then proceed to the conclusion of this one-week meeting. And I would like to call on Sergei Kilin and Gregory Vereshchagin, and to conclude with my participation in this meeting. Is Sergei there?
Okay, do you hear me?
Yes, very well, Sergei.
Okay. Okay. Hello to everybody from Minsk. Thank all the participants of the first Zeldovich virtual meeting. There were two principal organizers of this meeting, the ICRANet and the National Academy of Sciences of Belarus. I am presenting the National Academy. It was a great idea of Remo Ruffini to celebrate the memory of Yakov Borisovich Zeldovich, who was born in Minsk 106 years ago, and to celebrate this bright scientist by organizing the series of meetings. We were happy to be host of previous Zeldovich meetings here in Minsk. Unfortunately, due to the COVID-19, we have been to change the format of the meeting to virtual. Nevertheless, the conference was successful. Special thanks to Gregory Vereshchagin for all his great efforts to make this meeting interesting and successful. We had a lot of bright talks from key speakers and young scientists. Two short remarks from my side. We have a look more carefully into the side of quantum optics to increase the power of astronomy measurements. It's very great that some talks have been devoted to this problem. And also, probably it's understandable that we have to use all AI facilities to attack the data, the big data of the astronomy measurements. As for the next Zildovich meetings, we are ready to hold the meetings here in Minsk if it will be decided to continue to organize these meetings. Thank you to everybody, and hope to see you somewhere and probably in Minsk. Thank you, Remo.
Thank you, Sergei. And Gregory, can you make some summary result?
Okay, thank you. I think the meeting has, well, not so long history so far, but I think it's grown up quite a lot from a regional meeting of 2008, where few countries were represented, mostly Russia, some European countries, and Belarus, to the international level of the second and the third meeting, where we had much broader participation and, of course, more international audience. And finally, this year, quite surprisingly, even despite the emergence of the pandemic, we found very strong interest among the participants. We reached almost 150 participants this time. This is a breaking record for the meeting. And the meeting became truly global in a sense, because we had participants from virtually all the continents, including even Antarctica, if you take into account the report from IceCube. And of course, we are very happy that there is such a strong interest from international community to the meeting itself. I think we're witnessing important developments in many fields, especially represented in the sessions of space missions on Tuesday, on the early universe session on Wednesday, and of course multi-messenger astrophysics in the evening, and of course also Thursday sessions were interesting, but especially today the development on supernova very actively discussed. We will we'll do our best to continue this series of meetings, and of course Minsk, as you can see on the here on the poster, is the main gate, golden gate, let's say, of Minsk, and I hope all the participants will be able to see it also with their own eyes when they arrive to Minsk for the next meeting. And if possible, I would like to ask all the participants to turn on your webcams now. So this will allow us to make a screenshot of people, at least who survived to the end of the meeting. Please turn on your webcams.
Good.
Please keep going. We see about 34 participants now, so if we can have some more people, please.
Very good. Excellent. And of course, we will publish the proceedings in astronomical journal in Russia. And I thank everybody for this great collaboration. I think we are in a very difficult moment, but also a moment changing. Very big changes And fortunately, with ICRANet, we have been participating, collaborating in 3 major meetings on electronic connection, one from Taipei, one from Mexico City, Ibarra, and this one spread all over. I think it's a great opportunity. I would like to read only some of the messages that are coming in. Andrea Kotriova, to thank all organizers, speakers, and chairs for the interesting meeting. Thank you very much. Stay safe and healthy. Many greetings from the Czech Republic. Maria Pruzhinskaya, thanks a lot for the meeting. Chris Fryer, thanks a lot, the organizer, for an excellent meeting. Thanks, great meeting. And then Kirill Maltsev, thanks, great meeting coverage, a wide range of research fields. Konstantin Kastriev, thanks to organize conference. Diseases are temporary. Progress is eternal. This can be taken as a motto. And again, Manuel Homan, thanks a lot for the great organization. Oleg Zastiarsky from Ukraine, thanks you very much to the organizer. Well, I think this has been challenging, but it's a powerful method to keep in contact, to spread news, and we look forward the next year to the Grossman meeting, again electronically, very likely, unless something very beautiful will start that will not be electronic. But I think we are learning how to use very effectively these electronic connections in work at home, in work far away, and this is a new era. I think it will be necessary because people cannot spend too much fuel in the atmosphere of the Earth to fly to meetings. I think this is a very positive, very effective, very direct participation. And ICRANet will do all what we can to improve and expand. Thank you again to everyone.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you.
Thank you, bye.
Nice conference. Bye.